Okay. Alright, so let's go over the homework. So this is the first question. I'm gonna do it let's do it in blue. So the first one says find x, okay? So this one is pretty straightforward. I gave you that hint being, a squared plus b squared equals c squared. That's the Pythagorean theorem that I mentioned before. So what we're gonna do is we're gonna look for a and b. So this is a, b, c, right? And b is equal to 10 plus 5, which is 15, right? Because it's the same length. And a is equal to 25 minus 10 minus 8. So 25 minus 18, that's equal to 5, 6, 7. Okay? So c is equal to the square root of 7 squared plus 15 squared. So 7 times 7 is 49. 15 times 15 is 150 plus 75, which is 150 plus 75 is 225. Add that to 49. So c is equal to the square root of 274. Okay, you can leave it like that. Or I guess in this case it's x, right? Because I said find it. I called it x here, but we're using a squared plus b squared equals c squared. But in any case, this is your answer, square root of 274. And if you did that, you'd get about 16.5, right? So square roots, they're not really something that you can do in your head or do with a calculator. It's or you need a calculator to get to a good answer. The best that you could do is, it's got to be bigger than 15. So you would do 15 times 15, you get 225. Then you do it with 16 by 16. When you do that, you'll get 256. And then when you'll do 17 times 17, you'll get 289. And you know that it's in between 16 and 17 because it's 274, right? It's between 289 and the previous one. So you can kind of guesstimate that answer, but it's like 16 and some change. But just leave it at that. That's good enough. Okay. So now that you have x equals square root of 274, right, we'll do square root of 274. I said find the total perimeter. So total perimeter here, you have to add. So let's start here. I'll do this one in pink. We're going to start here. That's 5 plus 10 plus 10 plus 8 plus the square root of 274 plus 25. That's the total perimeter. You just add all of these up. So you're going to get 25, 50, 58, 58 plus square root of 274. Just leave it like that. Okay. Area. This one's a little bit easier to do. So as far as area goes, let's start blocking things off, right? We'll do them in terms of square. I'll do this one in red. So this one right here, we're going to block it off. This is a 5 by 10 square. So the area of this is 50, right? Because for rectangles, area is equal to length times width, right? We went through that last time. Okay, and we know A is equal to 7, right? So we have this side is 10, this side is 7, so that's 17. That makes, so if we want to find how much this guy is, this area, it's 25 minus 10 minus 7, right? And you should get 8, right? Because that also lines up with this guy. right? So now you have 8, and the total length of this guy is 15 because you have 10 here, you have 5 there, right? So now this cube is 15 times 8, which is 120. So we'll do that up here. 15 times 8. 8 times 5 is 40. Drop the 0, carry the 4. 8 times 1 is 1. Plus 4, 8 times 1 is 8. Plus 4 is 12. So 120. Right? So the first one, so now this one, this cube is 120. Okay? Now this one is a little bit easier to do. If you recall, for triangles, it's 1/2 base times height, right? Because remember, if you just took this as a square, you just pretend it's a square, you know the length is 7, you know the width is 15. So if this was a square, it'd be 15 times 7. But because it's a triangle, you divide by 2, because a triangle is exactly half the area of a square. And you can prove this to yourself by getting a square or a rectangle and just folding one corner over. You'll always be able to perfectly line up the edges, right? So now this is 1/2 times 15 times 7. So that is 15 times 7 is 105. Or you could do, 120 minus 15 because that was times 8. So 105 divided by 2, that's about 52.5, right? Because 105 divided by 2, you get 5 here, minus 10 is 0. Drop the 5, you get 2, minus 4, you'll get 1, and then 0.5, right? So 52.5. So the total area is 50 for this guy, 120 for this guy, and 52.5 for the last one. So that gives you about 222.5. And I didn't give you any units, but whatever, for perimeter, the units is, say everything is in feet, then this would be in feet. For area, it'd be feet squared, right? So this last question says, if 1 foot of fencing material costs $250, how much would it cost to buy fencing material with 10% sales tax? Okay, so now this one, we have to go back to the perimeter. I'm gonna round 270, the square root of 274 to 16.5, right? So 16.5 plus 58 is 74.5, okay? So I'm actually gonna just grab this question, move it down a little bit. Okay, so I'm gonna round, and I'll do this one green. Okay, say perimeter is approximately 74.5 feet, right? So all I did was I took this number and I rounded it to the nearest tenth of a foot. So if 1 foot of fencing material costs $250, how much would it cost to buy fencing material with 10% sales tax? So you know that you need about 74.5 feet of fencing material. So now we multiply this by 250, right? So 74.5 times 250, well, we can do this like this. So 74.5 times, so that's, well, let's just do 2.5. Make it simple I'm gonna simplify a little bit. 5 times 5 is 25. 5 times 4 is 20, 22. 5 times 7 is 35. Plus 2 is 37. Okay? and then drop a 0. 2 times 5 is 10. 2 times 4 is 8. We'll carry a 1 is 9. 2 times 7 is 14. So now add these up. We got 5, 2, 14, 15, 16. Carry the 1, 8, 1. So we're at, and we move it twice because there's 1 here, 1 here. So we're at 186.25. Now I'm going to verify this. 74.5 times 2.5. 186.25. Okay. So total for just this, for just the fencing material is 186.25. And then I said tax is another 10%. So we're going to multiply this by 1.1. Because if you multiply by 1.1, that's as if you're scaling up by 10%, right? It's the same. Multiplying by 1.1 is the same thing as multiplying by 1 and adding 0.1, right? If you think about it, right, you have x times 1 plus x times 0.1. You factor out the x, you get x times 1 plus 0.1, which is equal to 1.1 times x, right? So that's how I'm adding in the tax, and you can do this when you're at the store as well. I don't know what the sales tax is in Missouri or Kansas City, but in California, in LA County, it's about 10%. So this is how I do my math. Okay, so this one's nice and simple. You're gonna write 18625, 18625, 0. Add it like that. So that you're just multiplying by 1 on both times. So the second time you you add a 0. So you have 5, 7, 8, 8 plus 12, 13, 14. Carry the 1, 0, 1. So 204,875. And you're going to do it here. And, our cents only go to 2 decimal points. So we have to round. So this becomes 204.8 because it usually rounds up to the nearest cent. Okay, so you're at $204.88. That's how much it will cost for fencing material with a 10% sales tax. Okay, and then the last one says if labor costs are another $7 per foot, what's the total cost? So again, we go back to here, this number, 74.5. 74.5 times $7, because now we have to do labor. So parts is just 204.88. Labor, we have to do this. Make sure I'm still recording. Okay. So 7 times 5 is 35. 7 times 4 is 28, 29, 30, 31. 7 times 7 is 49, plus 3 is 52. Okay, so you're at $521.50. So that's how much labor costs. So parts, labor, and total is 521.5 plus 204.88. So 8 just goes down. 8 plus 5 is 13. 5, 6, 7, 8. Yeah, 13. Drop this decimal. 4, 5, 6, 0, 2, 5, 2 is 7. So $726.38. That's how much the total will be for this guy. Okay. So that's how much this is. Okay, second one. Shopping list. 6 cheeses, 10 breaks, 100 foot at 50 cents, and sales tax at 12%. Find total cost. So this is what I wanted you to do for this one. I said write a single equation to solve this. So I wanted you to do, final price is 1.12 times 6 times 275 plus 10 times 750 plus 100 times 0.5. That's what I wanted you to do. And how does this make sense? We're going to go one by one. Okay. 6 fuses at 275 a fuse. So that's this. 6 times 275 gives you the total price for how much the fuse is going to cost. 10 breakers at 750. 10 breakers at 750. 100-foot zero gauge wire at 50 cents a foot. That's 100 times 0.5. Okay? And then sales tax 12%. That's this guy right here. Remember how I said 1 plus 0.1 is as if you had 10% increase, right? Same thing. Now it's 12%. So we'll just do this as is. So I just wanted you to write the equation, but if we want to solve it, let's solve it. So 100 at 50 cents a foot, that's $50. Plus 750 times 10 is 75. Plus 275 by 6, this one I can't do in my head. 275 times 6. 6 times 5 is 30. 7 times 6 is 42. Plus 3 is 45. Oops. 45. 6 times 2 is 12. Plus 4 is 16. And then you move 2 decimal points, so 1650. Okay, 1650. So now we add. So this is 125 plus 1650, 50, 11, 2, 3, 4, 141.50. And now 141.50 times 1.12. Okay, so the first one is 0, 0, 1, 2, 3. 4 times 2 is 8, 2. And drop is 0, 0, 5, 1, 4, 1, 0, 0, 0, 5, 1, 4, 1. So remember, every time you go down, you add another 0. So now we get 0, 0, 5, 8, 5, 6 plus 8, 12, 13, 14. Carry the 1, 4, 5, 6, 7, 8. 4, 1 is 5, 1. And then there's 1, 2, 3, 4 past the decimal point. So we start here, 1, 2, 3, 4. That's the final decimal point. So 158.48. That's the total price. Okay. At this point, I would ask you if this makes sense. And the way that I would check my math is I would first look at my final answer, 158.48. And the first thing that I would do is, because it's 12%, I can very easily round and do 10% and then just kind of do things like that. So if I know that my final price is 141.50, let's just call it 142. And it's so much easier adding 10% to stuff because you just move the decimal point once, right? So you just add 14.2 to 142, and this is a lot simpler of a calculation, and you'll get 651. You'll get 156.2. It's about 10%. And you'll go down. You'll see 158 versus 156. Okay, that's reasonable, right? If 10% is this, then 12% should be close to it. So that's how you solve the homework. I think my biggest mistake for giving you this homework problem is this square root 274 number. But just don't get lost in the sauce sometimes, right? It's just sometimes you'll get lost in the weeds when it comes to your job. you're gonna do a lot of like estimating, right? The perfect numbers aren't gonna be really useful a lot. You're gonna have a lot of estimations, um, but I guess that's probably not useful when it comes to an exam. So you definitely want to be accurate when it comes to those, to at least the first decimal point or second decimal point. There's actually a part of math that is called significant figures, or sig figs, and there's a whole reasoning or whole theory behind how many digits are significant, and after that number of digits, they're no longer significant, and they just carry less weight. Um, I hated that, to be honest with you. I really did. But in my experience, usually carrying it four times past the decimal point is usually uh, more than accurate enough in most cases. But I have gotten, you know, exam marked down before because I just didn't do the multiplication with enough significant figures. Um, at which case, I went to the professor and I tried to get some points back. Uh, which, some people are nice enough and they'll do it. Some people are not. Just depends on what class. But yeah, I definitely got a life lesson one time when it came to that. So just need to be careful, right? Because when you're talking about like feet of wire, right, estimating to the tenth of a foot is really not helpful, right? Because wire is it's cheap, right? It's dirt cheap. But when things are very expensive, and you need to be accurate, to a certain degree, then of course, take as many decimal points as you need. Um, but that's an aside. So for today's lesson, I'm gonna revisit voltage and current with you, um, and we're gonna go through parallel and series resistances. So I'm just gonna go over what voltage, current, and resistance is. So voltage is potential energy. Potential energy, right? Um, just because there's voltage doesn't mean there's current, right? Just because there's current, if there's current, there's always voltage. But just because there's voltage doesn't mean there's current. What do I mean by that? When you have a battery terminal, right? You have your red, your hot, and your return, right? If you took a multimeter, it's rated for 12 volts, right? 12 volts. So you know that there's voltage here, because if you connected something from here to here, it would start to pull current. But right now, with an air gap, with the conductivity of the air is so highly resistive that there is no current flow between the positive and negative terminal, right? Because air is not conductive. You cannot conduct through air. Now, say this was submerged in water, all right? We'll put this guy underneath the water, right? Water itself is not conductive. Like pure water is not conductive, but the particulates in the water, like there's salt, right? Or contaminants in the water, that is conductive, right? And when uh, when you now that there is conductivity, there's something for so let's talk about resistance for a second. Resistance is the ability to impede the current flow, right? So air is highly resistive as far as electricity is. Like let's just think about conductivity in as a whole, right? Um, your pot, like when you're cooking, okay? Uh, would you cook? Let me try to draw a little campfire here. Right, say that's your campfire. Right, Shima, should you draw? When you cook, you use a pan, right? You use a pot. It's made out of some metallic material, right? Would you cook with a plastic container? Probably not, because a plastic container will melt, right? It's just not designed to cook. It will get hot, but I guarantee that the plastic will probably not get as hot as a metal pan would. At least, metal pan will get a lot hotter before melting, right? Thousands of degrees. But, for us, cooking is about 200 degrees Fahrenheit, 300 degrees Fahrenheit, somewhere around there. So metal is a very good thermal conductor, right? It conducts heat very well. There are a lot of plastic epoxies that can handle high temperature without melting, but they don't get hot. They're not very thermally conductive, right? So, like, I'll give you a perfect example. Glass, right? Would you use glass to cook your steak? Probably not. No, right? Glass can probably get pretty hot, but you don't see people with glass pots and pans, right? It's not the right material. So thermal conductivity is a good way for you to think about electrical conductivity, right? Because when things are, like, say for example, when things are wet, you have a wet stick. Will that burn very well? Probably not, right? Because the moisture in the stick reduces its thermal conductivity, right? Now we're gonna talk about electrical conductivity. So silver, I believe silver is the best electrical conductor out of all materials that we have. But it tarnishes, so we don't use silver, we use gold. Gold is the next best thing. So in a lot of high-end electronics, they gold plate and they use gold wire bonds to connect things. In houses, people usually use copper, right? They use copper wire or aluminum or something like that, right? Because they're all good electrical conductors. Um, like aluminum, copper, they're all good electrical conductors. Um, what is not a good electrical conductor? Um, I don't know off the top of my head what metals are poor electrical conductors, but I'm sure they exist. Um, the reason why I bring this up is because materials, the physics of materials is what kind of translates to resistance. So resistance is how easy it is for an electrical current to flow through a particular material, right? So the way things are created, they're like, if we have you have to think about the atoms, right? I'm blanking on how. Let me look at how many free electrons. So is do, 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 do. Mm. So I think I need to table this topic for a next lesson because it's gonna include a lot of chemistry. Um, because the reason why I was gonna talk about it is there's free electrons, right, for H2O, right? I believe oxygen has Uh, 6 electrons. Oxygen number of electrons. 1, 2, 3, 4, 5, 6, 7. Oh, it has 8. It has 8 electrons. But so how I remember it um, is oxygen has eight okay, so it does have 8 electrons, but the first two don't count because they fill up the first valence or first electron cloud, and so oxygen actually has 6 electrons in its outermost shell, and hydrogen has 1 electron. So when you add in a hydrogen molecule, it creates a lattice like this, right? And it's the so the way I remember it, which is again probably need to refresh my chemistry, is for the first electron shell you have 2 electrons, and every other electron shell you have 8 electrons, 8 electrons, right? So when you fill up the first shell, there's no free electrons, right? So these guys are full. This guy's full. Um, this is probably a bad thing to. Yeah, let me. Let's ignore that part. But let's go back. So resistance is how conductive material is, right? If it's poorly conductive, it has high resistance, right? If it's highly conductive, it has low resistance. Like plastic is not very well conductive. It has high resistance. Metal usually has good conductivity, low resistance, right? And current again is to calculate current. It's how many electrons pass through an arbitrary cross sectional area in a given amount of time. So it's basically how fast the electrons are flowing, right? So if you remember the Ohm's law, V equals IR. So voltage is equal to how many currents are flowing, or sorry, how many electrons are flowing through some given resistance, right? Because that's the potential energy needed in order to travel at the rate that electrons do, right? So if you have a material that is 10 ohms of resistance and you give it 5 volts, that means only half an amp is able to travel in that given amount of time. But of course, as you increase the voltage, as you increase the potential energy, and you keep the resistance the same, the current will increase because the higher potential energy you give, the more electrons can pass, like the more energy you're giving the electrons to run through this resistive material, right? I'll give you a perfect example. Think about voltage as your level of fatigue, right? At the beginning of your day, how many miles do you think you can run, right? You can probably run, say you can run 5 miles, on a good day, straight up in the morning. You get up, you fresh, you ate your breakfast, you're very refreshed, you can run, right? But as you go through the day, your energy levels go down, right? You did this, you did that, you have less energy. At the end of the day, you try running, maybe you'll get a mile out, right? You're doing the same activity. You're going through the same 10 ohms, right? You're running the same distance. But if you start out with less energy, you're only able to produce so much, right? So voltage is how much energy there is, how much potential energy you have. When you give an action or you connect a resistor or you have some resistive or some path to travel, it's going to figure out how much energy is available and translating that into um, how many electrons can pass through at what given time. So let's just talk about let's talk about something a little bit more visual, right? Here's your voltage source. So you have 10 volts, just to keep things simple, right? And I'm going to draw a resistor here, and I'm going to say this is a potentiometer, right? And what I'm going to do, I'm going to draw the current, right? Current through voltage. So if I was to draw resistance with current here, it's inversely proportional, right? With the same voltage, if voltage stays the same as uh, as R goes up, current goes down. Now, why is this? Why does this matter? Why does this matter? Effectively, what I'm trying to explain to you is an open versus a short, right? When I say there's an open circuit, that means infinite resistance. When I say that there's a short, that means zero resistance, right? So if you took your car battery terminal, like you go to your car, right? You have your positive terminal, your negative terminal. And you take your jumper cables, right? Just because you have jumper cables, say you have jumper cables, right? And you attach one side here and one side here, and you take the other side of your jumper cables and you connect them to each other. What will you see? You'll see a shit ton of sparks, because what you're doing is you're creating a short circuit. You're giving a zero path to ground, or you're connecting the terminals with such a little resistance that the current flowing through the line is so high that it's able to physically it's able to become physically realizable as sparks, right? When the current is that high, that's what happens when sparks are created, is because the current is so freaking high that electrons are traveling so fast, they're flying out, they're hitting each other and flying out into the world, right? That's what's happening. So when you have a short circuit, something's gonna blow, right? Say in your motor, you have something that's, or in your generator you have something that's supposed to be like you have a load, right? And your load short circuits, something's gonna blow up, right? You're gonna get a mass. That's why we have fuses, right? That's why we have a fuse, because in this situation, if you had a fuse right here, that fuse is a sacrificial piece. It's gonna kill itself. It's gonna evaporate. What is a fuse? Let's just talk about that for a second, right? A fuse is literally, if you take out your fuse, I guarantee it's gonna look something like this, right? It's gonna look like this, and then in the middle, it's gonna look like something like this, right? Now this is the housing, right? This is the housing, right? I don't want to. Maybe I'll highlight it. We'll do blue because I like the color blue. My fuses are blue green usually. Right? It's gonna be something like this, right? And if you look closely, what is this? What is this right there? Right? What is this? This is a very thin piece of metal film that is rated to only handle a certain amount of current. And once this current increases past its limit, it will get so hot that it melts. and when it melts, it's gonna be it's gonna not have a conductive path anymore, right? It's gonna melt itself and it's gonna die. But when this guy dies, everything else downstream is protected, right? So say you have your motor. Say you have your generator. Let's use generator, right? Say you have your generator. I'm gonna draw this, like, I'm gonna draw a generator like this, like this. Then I don't know what the symbol is for a fuse, but I'm gonna draw it as a box, fuse, right? And then here's your load. Here's your load, plus, minus, right? Say you have, excuse me. Say you have here, you had something important, right? Say you're using this generator to power your house, right? Or your car, or whatever. All right. All of the circuitry inside of here is only rated to have so much current. If the current here spikes, you have a high event here, like 40 amps, 40. Actually, maybe it's more realistic for it to be like 70 amps. This guy's gonna kill himself, right? He's gonna die, and he's gonna protect everything downstream. He's gonna protect everything, right? Now, if you have an open circuit, that's basically your battery is just a fuse goes from a short to an open circuit to protect against the case where there's a short circuit downstream, or there's an event downstream that damages, or that draws too much current, right? Okay, so I think that's enough about that. I'd like to think you got the idea. But if you have any questions, please, message me. It's not a big deal. I can talk about this kind of stuff for hours. Let's talk about let's go back and talk a little bit more about resistors in series, resistors in parallel. Okay, loads in parallel, loads in series, right? So a resistor in series is additive, right? If I had a 100 ohm resistor and then I gave it another 100 ohm resistor, the total is 200 ohms. Okay. But interestingly enough, if you have two resistors in parallel, say you have, right, 100 here, 100 here. Now this is 50, right? I know it's a little strange, but let's think about it for a second, right? Just so you know, the equation is resistors in parallel. R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over, actually I'm just gonna do plus dot 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 plus 1 over Rn for n number of resistors, right? So say you just have two, it's just 1 over 100 plus 100, 1 over 100. And then if you do that, you get 1 over 2 over 100. And then if you remember the equation I told you about, same, snap, flip, 1 times 100 over 2 is equal to 50, right? But how does this make sense, right? How does it make sense that you had 100 and now the equivalent is 50? Well, let's just think about it, right? If you have if you have the same amount of water, right? You have a bucket of water, right? And I have one siphon, right? And I say that this siphon is draining out 1 gallon per minute, okay? And I get another siphon, same thing, right? Now this one's drawing 1 gallon per minute. How much total am I siphoning out? 2 gallons per minute, right? So how much current going through, if it's the same voltage, say that there's 5 volt, let's go down here. Let's redraw it, right? Say that there's 5 volts and 100 ohms. How much current is flowing through here? It's 5 over 100, which is equal to 0.05, right? So that's 50 milliamps. 50 milliamps, right? Now, if I gave another resistor here, 100 ohms, it still sees 5 volts because potential energy is the same. It's the same. So just to back out, voltage is the same in parallel. Current is the same in series, right? So what I mean by that is if you have your battery source, right? You have your supply. I'm going to redraw a car battery. I'm going to draw a car battery, right? Everything your battery is connected to sees plus 12 volts, right? Everything. Whether it's this is your, say it's your fan, or it's your starter, or it's your radio, they all see 12 volts, right? Each of them draws their own current though. I1, I2, I3, and how much current is here is I total, but they all get 12 volts, but they get their own current, right? So current is the same if it was in series, right? Everything in series with this line gets the I1. Everything in series with your starter gets I2. Everything in series with your radio gets I3. They branch off, right? But the total voltage, you know, it's in parallel, it's the same. Current is the same in series, right? So go back to this figure. This sees 5 volts, this sees 5 volts, right? So then this will now see also, this will get its own 50 milliamps. This will get 50 milliamps. And now before, your supply only had to supply 50 milliamps, but now it's giving 100 milliamps, right? Because 50 plus 50 is 100. So it's as if instead of having a 100 ohm resistor, you put in just a single 50 ohm resistor, right? That's what equivalent resistance means, right? You're finding you have some um, resistance, and you're finding what that equivalent is, right? You're trying to replace a network of resistors with a single resistor. So let's do something a little bit more complicated. Right, if I did resistor here, resistor here, resistor here, resistor here, resistor here, right? I'll call this 10, 10, 10, 10, 10, right? And this is 10 volts. And if I said find I1, I2, I3, right? I said find those, right? The way that you would do that is you would break it up into equivalent resistance first, right? So this I3 is in series, right? So I'm going to redraw it. And this one is 20 ohms because 10 plus 10. But now this is in parallel with 10. So 1 over 1 over 20 plus 1 over 10 is 20 over 3, right? Actually, you know what? I'm going to actually make this easier for myself. And I'm going to change this resistor to be 20, right? So now when I have 20 this will now be 10. Right? So now I have 20 in parallel with 20. I know that's 10. 10 in parallel with 10. I know that's 5. This is 10. This is 10. So the total current, I1 plus I2 plus I3, is equal to, V divided by R equivalent of the entire thing. That's not a Q, that's a G. There you go. And my V is 10 volts. And now what I did is, you saw, 10 plus 10 is 20. 20 in parallel with 20 is 10. 10 in parallel with 10 is 5. 10 in series with 5 is 15. So my total current is 10 over 15, right? Which is 2/3 of an amp, right? 2/3 of an amp. So now the fun part starts, right? I'm going to change a different color. So I know here, at this point, I'm getting 2/3 of an amp, okay? So at this point, I know I'm getting, actually maybe it'd be better if I do it this way. At this point, I know I'm getting 2/3 of an amp. And now look, I see an even split. I see 10 ohms this way, 10 ohms this way, right? This 10 ohms is real. This 10 ohms is an equivalent resistance, right? But as far as I'm concerned, half the current goes this way, the other half goes this way. So I'm going to get 1/3 of an amp here and 1/3 of an amp here. All right? So now I know that I1, the current going through this 10 ohm resistor, is 1/3 of an amp. And now I'm going to go back up here. I'm going to realize that at this point here, I'm getting 1/3 of an amp. And again, I see an even current split. 20 here, 20 here. Which means that this is getting 1/6 of an amp, and this one's getting 1/6 of an amp. So now I know I2 is 1/6 of an amp, right? And I3 is just the remaining, right? It's just the remaining 1/6 of an amp, right? So you have a starting current total, you know it's 2/3 of an amp. And now you know that I1 is 1/3, I2 is 1/6, I3 is 1/6. And if you sum those up, you'll get 2/3. Okay. I think that is sufficient for this video. I don't want to go too far in too much detail. Since you're not here to ask questions, I don't want to move too quickly. But definitely let me know if there's any questions. Let me know if there's anything in particular you want to talk about, or if there's something that you didn't understand, and we'll go over those in detail at our next session, or text me, and I'll get back to you with something. Alrighty.